Hi guys! Let's see how I do with my goal of an 8-minute video. No time to waste, so let's get straight to it. Exponential functions are very important in terms of their application. And the reason why we want to learn exponential functions is because they happen very often in the real world. One of the most prevalent places that we see exponential growth or decline is when we talk about interest. So the first thing that you see on your worksheet is actually the formulas for compound interest. When we talk about compound interest, this is interest that accumulates over time. Those formulas, possibly in Algebra 2, you have seen exactly how they're derived. For right now, we are going to use them as they are. If you have n compoundings per year, then you would use the formula A is equal to P times 1 plus R over n to the n to the t power. It might be helpful to add the meaning of some of these variables. So here, A is always going to be your initial amount. I'm sorry, A is going to be your amount right now. Or whenever you're calculating it for. P is going to be your initial amount. And since we talk about amount, we can put initial dollars. R is always going to be your interest rate. N already comes here and is the number of compoundings per year. So for example, if you are compounding interest monthly, then N is going to be equal to 12. Since you are compounding it monthly, that rate is always given as interest rate. It's always given yearly, which is why in the formula we have to do the yearly rate divided by how many times you're accumulating that interest. So N represents the number of compoundings, or how many times is your interest paid out to you. Lastly, T represents time in years. Okay. Note that these variables are the same for continuous compounding. The difference is that with continuous compounding, your interest accumulates every fraction of a second of the time. And that adds up to P times E to the R times T rate. So the rate goes in the exponent, and so does T in years. Another very common application is the half-life problem. So let's go ahead and add a formula that we can use with half-life. With half-life, our formula is A is equal to A0, which represents the initial amount, times 1/2 to the T over H, where T once again represents the time, H represents the half-life. Let's get straight to our problem. Let Q represent the mass in grams of radium. Radium is just a type of material, and you see its chemical number in the way that you would write it in chemistry. Its half-life is 1600 years. The mass of radium present after T years is given by the following equation. We are asked to find the initial mass, and then what is the mass after 1000 years. To go ahead and calculate that, since T is the time in years, to find the initial mass happens when T is equal to 0. Well, in that case, we can go ahead and calculate in our equation. It is given as Q in here. So we have Q is equal to 16 times 1/2 to the 0 over 1600. Well, 0 over 0 divided by 1600 is still 0. And anything to the 0 power gives you 1. So we're back to 16. Please note that this 16 was actually equal to what I noted as a null up here, or A0. This A0 always will represent your initial amount. So even if I didn't do the calculations, automatically I should be able to say that the initial mass is 16 grams. And then to calculate what happens after 1,000 years, that means that T is going to be equal to 1,000. Well, it looks like I know everything I need to know to calculate Q. Q is going to be equal to 16 times 1/2. And then instead of T, I'm going to input 1,000 over 1,600. This is definitely less than a half-life, which means that my answer should be more than 8. When you input that in the calculator, you get that it is approximately equal to 10.37. This amount is measured in grams, so after 1,000 years, starting with 16 grams of radium, after 1,000 years, you will have 10.37 grams. To look at a second problem, please pause the video and read the problem. We're given the population growth rate is 8%. We are given the actual equation for this population growth. Let's go ahead and answer the questions. To find the initial population, well, from the formula above, I told you that this number at the beginning is always going to be your initial population. So automatically, you can say that it is 450,000 people. To find the population after 20 years, we are going to find population when T is equal to 20, and that is equal to 450,000 times e to the rate of 0.08 times 20. Note that the whole thing is in the exponent. When you're calculating this in your calculator, just be very careful. Make sure that your exponent is all in parentheses. Otherwise, your answer will not be correct. That is approximately 2,228,865 people. Quite a big growing rate, I have to say. And then for the last part, we have to graph that function. As always, our growing rate is going to be at that starting value of 450. I'm going to input the population in thousands. Let's go ahead and label those. So when you're labeling it, this will be population in thousands. I'm going to do that every 2 squares are going to double this initial rate. So this is going to be 900,000. The next one is going to be 1,350,000. The next one is going to be 1,800,000. And then the last one is going to be 2,250,000. Okay? And then our x-axis represents time in years. And I'm going to do that every 3 squares is equal to 5 years. So that can be 5, that could be 10, that could be 15, and then we have 20. Really, we only need these 2 points. I do know that I have a point at 0 and 450. But exponential, instead of 0.1, I'm going to multiply this by my initial amount, and I have a point at 0, 450,000. My next point, we calculate it right here. At 20 years, it is a little bit less than 2,250,000. So I'm going to estimate a point right there. And finally, to sketch our graph, we do know that we have an exponential growth. So we can do a nice little curve that's going to get steeper and steeper as it goes. And that's all I have. Man, I am 2 minutes over. I'm not redoing the video. Sorry, guys.